Okay, so having seen the solution to exercise 7, having completed that, we now turn to exercise 8. So this says to check that n is a prime number, n is some positive integer, prove that it is sufficient to show that it's not divisible by any prime number p satisfying p less than or equal to root n. So let's just see what this exercise actually means. It sounds a little confusing at first, but let's take an example. Say n equal to 101. Suppose we want to know whether 101 is a prime number or not. What we will do in search for a prime factor of n, for this particular value of n, we will look at the primes that are less than n. Now there are these 25 primes less than 101. Okay, so what we will do here, we will see one by one whether 2 divides 101, whether 3 divides 101. If we find a prime number in this search that divides 101, then it is not a prime number, because then it has a factor, prime factor, that is less than the number itself. Otherwise it will be a prime number by definition. However, this exercise says that we need not go all the way till 97. Okay, we can check only for those primes that satisfy this inequality. Now, is it somewhat effective? I mean, does it reduce the labor? In this case it does, because you see 100 is less than 101. Now since both these numbers are positive, so square root of 100 is less than square root of 101. Now square root of 100 is 10. And since we want to look for prime numbers which are after all integers less than or equal to n, so we have to look for only those prime numbers that are less than 10, because 10 itself is not a prime number, and there are only 4 of them. So you see whether any of these divisibility conditions is true. We can check that none of these 4 prime numbers divides 101. That's why by this exercise 101 is a prime. So instead of looking for such divisibility relations for all these 25 primes, the part has been reduced to verifying only 4 divisibility relations. So that's how this exercise reduces the work. But of course, if n increases, so does square root of n. So ultimately it becomes inefficient. However, this is a property of prime numbers. So we need to prove this now. So let's now solve this exercise. Okay. So what we want to show, that to see whether this is a prime number, it's sufficient to show that it's not divisible by a prime. Okay, so if we translate this exercise in this way, to show that this is a prime number, n is a prime number, it's sufficient to prove that n does not have a prime factor p that satisfies this inequality. That's what we want to prove. Okay, so let n be not a prime number. In number theoretic terminology, such numbers are called composite. You already know that. Okay, then n is equal to AB for some, since n is not prime, so n will have non-trivial factors. So I can assume that n can be written as AB, where both a and b, each one of them is neither 1 nor n. For some integers a and b, satisfying this. Okay, a and b are proper factors. None of them equals n or 1. Now, a and b, as far as the relationship, the order relation between them is concerned, one of them is less than or equal to the other. That is always true. So, without loss of generality, assume A is less than or equal to B. A and B may be equals. In that case, n will be a square of some integer. Okay. Now, if I multiply both sides of this inequality by A, what do I get? On the left hand side I get a square, on the right hand side I get ab. And why is the inequality preserved? It does not change direction. It's because a is a positive integer. So multiplying by a positive number does not change the inequality. Does not change the direction of the inequality. And what is ab? Ab is n, right? Hence, or which implies a is less than or equal to square root of n. Okay, it's because we can take square root on both sides because both a and n are positive. Now, since a is greater than 1, here we have a greater than 1, there exists a prime number p such that p divides a. How am I concluding this? I am concluding this by using the fundamental theorem of arithmetic. It says that any positive integer greater than 1 has a prime factorization. So it's a consequence of that theorem that a has some prime number as its factor. Now, this implies p divides n. Why does p divide n? Because a divides n and p divides a, that's why p divides n. And p is less than or equal to a, which is less than or equal to square root of n. Why is p less than or equal to a? That's because p is a positive divisor of a. And since a is less than or equal to square root of n, so we have this inequality. So what have we proved here? If n is not a prime number, then it has a prime factor p, which satisfies this inequality. That means if I take all the prime numbers less than or equal to square root of n and none of them divides n, then n cannot be composite. It's the contrapositive of this statement. So here what we have proved is this: n is not prime implies, or let me write it formally, let me make it a part of the solution. So we have proved that if n is not prime, then it has a prime factor. You can either write factor or divisor, they mean the same thing. Prime factor p satisfying p less than or equal to root n. Now this is an if-then statement. This is what we have proved here. If n is not prime, then it has a prime factor less than or equal to its square root. What is the contrapositive of this? Contrapositive is, you see here, this part is the hypothesis of the implication. If then means implication. This is the conclusion. So the contrapositive will be negation of the conclusion implies negation of the hypothesis. That is, if n has no prime factor p satisfying this, in other words, if no prime number p satisfying this inequality divides n, then n is prime. That is, it's not the case that n is not prime. That means n is prime. In other words, that's what we are going to write now. If n is, oh sorry, not this way. If for every prime number p less than or equal to root n, we have p does not divide n, then n is a prime number. So this completes the solution. Let's now move on to the next one. It also involves a property of prime numbers that is sometimes helpful. Exercise 9. Show that n greater than 1 is a prime number. Again, this is again a condition for a number to be prime, but this is an equivalent condition, if and only. But this one, the previous exercise, was only a sufficient condition. It says that if a number is not divisible by the primes which do not exceed its square root, then it has to be a prime. Not the other way around, okay? Not necessarily. Show that this is a prime number if and only if. So if and only if means double implication. It is true in both the ways. for any a, or any a means for any integer a. Either a and n are relatively prime or n divides a. Yes. Okay, so this one. Solution. So what this says is that if n is a prime number, if n is an integer greater than 1 and it is a prime number, then for any integer a, either a and n are relatively prime or n divides a. Conversely, if this condition is true for every integer a, then n has to be prime. Okay, so here we have to prove two things, two implications. So let's have a look at what shall we do. Let us take at first let's take this as the hypothesis. So we prove that if n is prime, then this happens. So first assume n is prime. Okay, n is a prime number, but prime number is noun. When we say prime, it's adjective. Okay, so assume n is prime. Let a be any integer. A can be any integer. A can be 0 also. Okay. If n divides a, now for this a we have to prove that either n divides a or a and n are relatively prime. So if n already divides a, then one of the conditions is true, then there is nothing to prove. So assume n does not divide a. Okay. We have to now show that a and n are relatively prime. Right? Let okay, instead of writing d or anything, I can directly conclude, right? N does not divide a and n is a, oh yes, yeah, I get it. Since n is prime, the only positive divisors of n are 1 and n. That is the definition of a prime. The only positive divisors of a prime number, since for us prime numbers are positive, are 1 and that number itself. Okay, so these are the only positive divisors of n. Since n does not divide a according to our assumption, the only common divisor, although we have not formally defined the term common divisor, we have defined greatest common divisor, but you can understand what I mean by common divisor. I should not really write this without defining it. However, you can write it more formally like this. So what I am trying to say here, okay, let me just first write it. Of n and a is 1. So here what I am trying to say is that if you have an integer c which is a positive number and which divides n and a, then c is a common divisor of n and a. The only, oh, I should include positive here, because otherwise I will have -1 also. The only positive common divisor of n and a is 1, because n already has only two positive divisors, 1 and n. Among them, n does not divide a, so n itself cannot be a common divisor of n and a. So the only possibility is 1. So that is the greatest common divisor. Hence, so either this is true, where is it? Either this is true, or if this is not true, then this is true. So in any case, we have either this or this. So this is one part of the solution. Now we prove the converse. Conversely, what do we have to prove? We have to prove that if this thing is true, if for every integer a I have either this or this, then n has to be a prime number. So conversely, assume that for any integer a excuse me, we have either this condition or this. We have to prove that n is a prime. Suppose that's not the case. Suppose n is not prime, then just like the previous exercise, if n is not prime, then n can be written as a product of two integers a, b for some integers a and b satisfying this. Okay. Now, oh, no, I cannot take a and b here because I already have a here. Let's take use some other symbol. Let me use alpha and beta. Okay. Now, note that n does not divide alpha. N does not divide alpha because alpha divides n. If n also divides, okay, n does not divide alpha, why? We have to say it's not that obvious. Not that n does not divide alpha, as otherwise n divides alpha and alpha divides n would imply, because n and alpha are both positive, so they have to be equal, n equal to alpha, which in turn would imply if n is equal to alpha, then beta will be equal to 1. But this contradicts this condition, this inequality, that beta has to be greater than 1. That's why n cannot divide alpha. Okay. Now note that n does not divide alpha. Also, it's not quite over yet. N does not divide alpha. At the same time, the greatest common divisor of alpha and n is equal to alpha. Why? Because alpha divides n. So alpha is a common divisor of n and alpha, and any common divisor of n and alpha also divides alpha, because alpha is the greatest one of them, right? Any divisor of alpha has to be less than or equal to alpha. So that's why this is equal to alpha and this is not equal to 1. Why? Because alpha is greater than 1. So the assumption that we have made here, that for any integer a, we either have a and n as relatively prime, or n divides a, is violated by this particular integer alpha. We neither have n dividing alpha nor have n and alpha relatively prime. So this contradicts our assumption or hypothesis, same thing. So the last supposition is wrong. What is the supposition? That n is not prime. So that means n has to be prime. That is, n must be prime. This completes the solution. Okay. Now after this, exercise 10 involves mathematical induction. Okay, let's just have the statement of the exercise first. Assuming that any non-empty, assuming that any non-empty set of positive integers has a minimal element. What is this? This is the well ordering principle that we already know to be, or we have assumed to be true for positive integers. You take the set of positive integers and you take any non-empty set in them, it must have a smallest element, a minimal element. Has a minimal element. Proof. Based on this assumption, we have to prove these two versions of the induction principle. So there are two subdivisions. A, if the proposition, oh, my background noise, if the proposition P is such that number one, this is how Herstein presents it, so I'm basically copying it. P of M naught is true, and number two, the truth of Pn minus 1 Pm minus 1 implies the truth of Pm. If these two conditions are true, then Pm is true for all m greater than or equal to m not soluble. Okay, so this version of induction, instead of starting from the first natural number, for us now, if you recall the assumption that we have made while talking about the set of natural numbers, for Herstein it starts with 1. For Terence tau it starts with 0. So usually Herstein's induction will start with 1. However, this one says that it can start anywhere at any positive integer. So m0 is one such positive integer. Okay, he doesn't say explicitly anything about m0, but it's as understood that it's a positive integer. Okay, this is one thing, and the other one is the strong version of the same thing. If the proposition P is such that, again, there is the first condition and the second one. The first one is same, Pm0 is true. The second one, however, is stronger than this one. Let me write it here. Pm is true whenever Pa is true for all A satisfying for all A such that satisfying same thing, m0 less than or equal to A strictly less than n. Okay, so here the assumption that P is true for all such A starting from m0 until m. So not only for m minus 1 but for all the previous A's, A values. Then the conclusion is then Pm is true for all m greater than or equal to m0. Now we have already gone through the many different versions of the induction principle in our analysis videos from Terence Tau's notes. So for the solution I refer to that. For both the parts, see exercise 222 within brackets I write tau. It means it's from analysis 1 and analysis 2. There is one more part of that book or of those notes. So when you see this thing, we will make this type of references more and more. Then you will have to understand that it's from analysis of tau. When you see Herstein somewhere else, like this, then you have to understand it's from this book. Okay. So for us it's done. Okay, let's now move on to the 11th exercise. I didn't write exercise. It doesn't matter, but we have to be consistent. Prove that the addition, okay, yes, this one. We left it there, right? Prove that the addition and multiplication defined in Jn are well defined. When we define these two operations in Jn, there we discuss what well defined means. Okay, now, and there we left it like that. Now we have to prove it. So we now know what we have to do to prove this. Let I1, so these are congruence classes modulo n. I2, J1, J2 are 4 congruence classes modulo n such that these two are equal. I1 is equal to I2 and these two are equal.